SwayamPrabha. Digital India. Educated India.
Hello everyone. So we get into now module 9 of this class where we talk about modeling and simulation. So far we've been learning a lot of theory about the turbulence, scales, energy cascade, equations, averaging the equations. We looked at how to represent these through Fourier transforms, model spectrum, what the energy spectrum means in terms of the different scales, dissipation spectra, how the energy is contained in the different ranges, how most of the energy is contained in the large scales, and the small scales are mostly responsible for dissipation, the inertial subrange. A lot of concepts have been learned. Now, as much as all the theory was interesting, now we need to apply to it to specific problems. We need to apply these to specific problems. So the modeling and simulation part becomes very important, right? How do you model the turbulence and how do you simulate the turbulence? So I try to use these two words very carefully when I say the word modeling versus simulation. Now we tend to sometimes use the words modeling and simulation as in one for the other, modeling in place of simulation or simulation in place of modeling. But however, simulation actually means you are resolving the flow exactly. That's what simulation is. And modeling means you are making an approximation. So simulation means you're resolving the flow, isn't it? You are accounting for the flow exactly. Whereas modeling is you are making an approximation and coming up with a solution. So we have to be using these terminologies very carefully because modeling is not the same as simulation and simulation is not the same as modeling either. And we will look at both of those in this particular module. So here we try to cover the challenges involved in understanding and predicting turbulence, the modeling approaches that are out there, which means that will take us to some of the criteria for, appraising models, the level of description, completeness, the cost of using certain models, range of applicability. We will look at accuracy, and for the most part we will spend most of this module on direct numerical simulation or DNS. And as part of this we will learn about homogeneous turbulence, pseudospectral methods, the computational cost associated with it, and so on. So let's get into it. So most of the information provided in this module is again from Pope's Turbulent Flows book. So we have briefed upon some of the challenges involved in understanding turbulence. Here we are going to specifically be discussing the challenges involved in modeling turbulence or simulating turbulence for that matter. I used the word modeling and simulating in indicating different meanings altogether, and I'll talk more about it as well. So the ultimate objective here in all of this, in coming up with a model, in coming up with a prediction, is to obtain some kind of a tractable theory or model that can be used to calculate quantities of interest and practical relevance. Maybe the velocity field is of primary importance to understand. Then we need a model or theory to understand that velocity field. Maybe it's not velocity. Maybe you just need to know how much turbulent kinetic energy is there in a particular space of your device or your flow field. What is the turbulent kinetic energy in that flow field? Then we need a model or theory that can predict that. Sometimes we need to know how the temperature evolves with time. Does your model or theory accurately predict that? That is what we need to know. So that is our objective, isn't it? But what is our challenge? Our challenge is what is called the turbulence problem, right? As we call it, the turbulence problem. What is the turbulence problem? There is no simple analytical theory to predict turbulence. Unlike for laminar flow, which at least for very simple kind of flows, you can get the analytical solution. In turbulent flows, you cannot get that. So solving it by hand, right? Coming up with an analytical solution, solving it by hand is impossible. Mainly because the nonlinear term in the Navier-Stokes equations is dominant in turbulent flows. So the nonlinear term makes the analytical solution completely impossible to obtain. In which case, we will need a computer to solve it. We will need digital computers to solve it. This is what brings us to a model. Now, to come up with a model, it's not that easy. Sometimes you will need an approximation for it, and then you will have to validate that approximation. Is that approximation valid for all kinds of flows in all regimes? That needs to be assessed. What is the cost associated with this model? How accurate can this model be when you compare to experiments? The range of applicability, those are all the questions we will need to answer. The objective is clear, but the challenge is the turbulence problem, isn't it? So that is where you have a computer model coming in. Now here I'm talking about a computer model, but what I mean to say is could be the theory or the model that you are implementing in a digital computer to solve for the problem. Now what makes it so difficult, right? What makes the turbulence problem, the quote-unquote turbulence problem, so difficult? And we've discussed this on many levels multiple times. The velocity field that we are discussing here, u, shown in bold here, u of xt, where x is also in bold, it's a position vector in bold because it's a 3D vector. And then you have the velocity field which has three components, u, v and w. And you have this velocity field which is 3D and time dependent and what we call random. It seems random to us, right? It is not a random phenomena, but it seems random. But however, its behavior is like it is behaving like a random variable. So that's one major challenge. Second, the largest turbulent motions are almost as large as the scale of the flow, meaning the width of the flow or the characteristic length of the flow, and therefore are affected by the geometry. So if you think about a jet flow, fluid is coming in through the nozzle, the larger scales are comparable to the diameter of the jet, diameter of the nozzle. Flow over a cylinder, the larger scales are comparable to the diameter of the cylinder. Flow in a channel, the larger scales are comparable to the width of the channel. So that is what we mean by they are completely determined by the geometry or by the boundary conditions. And so as a consequence, you have a wide range of length scales. That takes us to our third point. You have a wide range of length scales because your smaller scales are orders of magnitude less than the larger scale. Orders of magnitude. That means you have a large range of length scales that you need to account for, that you need to predict, that you need to calculate in order to understand this. And because you have a large range of length scales, you obviously have a large range of time scales because every length scale is associated with its own time scale. So you have a large range of time scales as well. That means to resolve your turbulent flow temporally, you will need to resolve it in time as well. So that's your third challenge. Your fourth challenge is something that we are all familiar with. It is the nonlinear convection term in the Navier-Stokes equations and the pressure gradient term. So the nonlinear convection term, what does that do? It makes getting an analytical solution impossible. Impossible. So you have the nonlinear term which is responsible for the velocity gradients, which is responsible for what we called the macro mixing in turbulence, isn't it? The fact that turbulence is enhanced diffusion, we call it enhanced diffusion, although technically it's not diffusion, but we are calling it enhanced diffusion because the outcome of that velocity gradient, nonlinear velocity gradient term in the Navier-Stokes equations is the same as what happens during molecular diffusion. The outcome, the mechanism is different. These are our challenges. Again, the velocity field is 3D, time dependent. You have a large range of length scales. The largest scale being of the order of magnitude of the characteristic length of the flow, and the smallest scale being what we call the Kolmogorov scale, isn't it? So you have a large range of length scales and as a consequence, large range of time scales. That's your third challenge. Your fourth challenge is the nonlinear convection term and the pressure gradient term. The viscous term, it's a second derivative, it's still linear. The nonlinear convection term, it's a nonlinear term, so that makes it challenging. And the pressure gradient is obtained from the nonlinear convection term, so that has its own challenges. So these are some of the challenges that we will need to consider when coming up with a model or a theory. And that is what makes it so difficult, isn't it? So, in a turbulent flow simulation, you have the equations which you solve for to obtain a time-dependent velocity field that represents the velocity for one realization of turbulent flow. What do I mean by that? U of xt represents one realization of turbulent flow. One realization means one repetition of the experiment. One repetition of the experiment. And the solution that you get by solving the Navier-Stokes equations gives you U in bold, U as a vector, as a function of x and time, and you are getting one realization. So that is what happens in a turbulent flow simulation. And notice here, I am saying simulation. That means I am solving for U exactly. I am resolving all U. I'll talk about the details of how I can do that in this module over the next few classes. But what I mean to say by a simulation is that I am resolving the entire velocity field, and the velocity field that I'm getting is one realization of a turbulent flow, one repetition in a turbulent flow experiment. In contrast, in a turbulence model, what I'm doing is the equations solved for are mean quantities. For example, mean of U, Ui Uj mean, and epsilon, which is the dissipation rate. What does Ui Uj mean? The Reynolds stresses. So I should point out that what I refer to here as the turbulence model is a RANS-based approach. Remember, I have three approaches, right? DNS, which is direct numerical simulation, LES, which is large eddy simulation, and RANS, which is Reynolds averaged Navier-Stokes. Notice that the top two uses the word simulation. Direct numerical simulation, large eddy simulation. So here, direct numerical simulation solves for all the scales. We'll talk about this in more detail over the next few classes. Large eddy simulation simulates all the large eddies. So it is still simulating. Whereas the Reynolds average Navier-Stokes, that has no word simulation in it. It is a model. This is a simulation. And this is also a simulation. So the RANS type model, it's a turbulence model. Here, what the RANS approach does is it solves only for the means. So U mean, Ui Uj mean, and the dissipation rate. The dissipation rate is a single quantity. There's no question of a mean coming into play there. It's a single quantity, so that is just the dissipation rate. Moving on, the two simulation approaches are direct numerical simulation DNS and large eddy simulation LES. Isn't this what I was just saying, right? Simulation means you are resolving U for every realization of the turbulent flow experiment. And DNS and LES do that. Direct numerical simulation and large eddy simulation respectively. In DNS, The Navier-Stokes equations are solved to determine u of xt for one realization of the flow, and because all length scales and time scales have to be resolved, because if I have to get u for one realization of the flow, one repetition of the turbulent flow experiment, if I have to get that, that means I have to resolve each and every length scale of the turbulent flow and each and every time scale of a turbulent flow. What do I mean by that? My grid size in direct numerical simulation has to be able to cover all the way from the characteristic length scale of the flow, which could be the width of the nozzle, the channel width, the cylinder width, the diameter of the pipe, the diameter of the cylinder, and all the way from that is the largest scale, to the Kolmogorov scale. So my grid has to be small enough to account for the Kolmogorov scale. Only then can I make sure that all length scales and time scales are resolved. Kolmogorov scale, I consider it to be the smallest turbulent length scale. So because there is this wide range of length scales and my grid has to be good enough to account for the largest length scale to the smallest length scale, the Kolmogorov scale, DNS is going to be computationally extremely expensive. And because the computational cost increases with RE cube, we will see that. In fact, the computational cost increases as a function of the third power of the Reynolds number. So imagine if you are going from a Reynolds number of 100 to 1000, your computational cost increases 1000 times. Just by going from a Reynolds number of 100 to 1000, your computational cost is increasing 1000 times. So that means your cost gets extremely expensive for DNS of a very realistic flow. Why do I say that? A realistic flow, what I mean by a typical engineering flow. A typical engineering flow will have very high Reynolds numbers. So the computational cost associated with that would be very high. So typically this approach of DNS is restricted to low to moderate Reynolds number. Even to date, even with the computing resources being increased significantly over the last decade, DNS is still not applicable to very realistic flows. Not every realistic flow anyway. We have made a lot of improvements over the last 20 years, yes, especially because computers have gotten much faster. We have been able to use computing clusters. Thousands of cores, millions of cores have been used for single simulations in order to run DNS. And yes, we have made progress, but even then, DNS, the applicability of DNS to very realistic engineering flows is limited. Has it been done? Yes, sure. But it has not been done to the same extent as we would want it to. So DNS has its limitations, mostly related to computing resources. In LES, on the other hand, large eddy simulations, the equations are solved for a filtered velocity field. All right, a filtered velocity field. Now, what do I mean by that? This is representative of the large-scale turbulent motions. So it does not represent the small scales, it represents the large scales. The equation solved, here you would need to include a model to account for the small scale motions, which are not directly represented. So what I mean by that is, if you have a grid, okay, so a representative grid like this, and if you have the grid is in such a way that in LES, the scales are going to be, you are going to have a grid that is good enough to represent the large scales, whereas you're going to be missing all the small scales in between. On the other hand, this is for LES, right? On the other hand, for a DNS, okay, what I have is the following, and even more, isn't it? As follows. And then what happens is, I have this motion which I can obviously get, and I have this motion which I can get as well, because my grid is able to get that. So both of these are simulation approaches. The LES approach is, you would say, is a part simulation process because it is only simulating the large scales. It is still simulating it though, it is still resolving it though, so it is called large eddy simulation. On the other hand, if you think about a RANS approach would be something like this. That would be it. That would be the grid. So any motion is not even accounted for. But it doesn't matter. Why? Because you're only accounting for the means. You're only accounting for the means. The Reynolds stresses, which are the means again, the dissipation rate, the U mean, you're only doing that. So this is a RANS approach. I hope you're understanding what I'm saying. So this is what the LES does. The LES is solving for the filtered velocity field. So it is solving for the filtered velocity field of one realization of a turbulent flow experiment. Not U, but U bar, as in U bar, U filtered, for one realization. So essentially, if you take a turbulent flow experiment, you get one realization by measuring it. You take that velocity field and filter it. Take it through a high-pass filter. I'm sorry, not through a high-pass filter. Take it through a low-pass filter where you have all the low frequencies coming through. If you take it through a low-pass filter, that is what will lead to the U bar, the filtered velocity field. That is what you're solving in LES. So what you're solving is the filtered velocity field equations. Now, because you're only accounting for the large scale motions, something has to be done for the small scales. That is where a model comes in. And that model is actually called, we'll discuss this in detail, but that model is actually called a subgrid scale model. The next module talks about LES in detail, so we will discuss this. Subgrid scale model, or SGS as we call it, SGS model. So these are the two simulation approaches. And finally, you have the modeling approach, which is the Reynolds average Navier-Stokes, which involves the solution of the Reynolds equation, right? We derive the Reynolds equation by averaging the Navier-Stokes equation to determine U mean and the Reynolds stresses. So you have three approaches essentially: DNS, LES and RANS. DNS and LES are simulation approaches and RANS is a modeling approach. DNS being a fully simulation approach, it resolves all the length scales and time scales. And because it resolves all the length scales and time scales, it is computationally very expensive. Whereas LES is still not as expensive as DNS, because what it does is it only resolves the large scales. The small scales it models. So if you consider DNS versus LES versus RANS, the computational cost keeps increasing as you're going from RANS to LES to DNS. The computational cost keeps increasing as you go from RANS to LES to DNS. And the accuracy also keeps increasing as you're going from RANS to LES to DNS. So then, based on the problem that you are solving, you will have to make a judgment on which of these approaches is right for you. So the accuracy keeps increasing from RANS to LES to DNS, and that is clear from the grid that I had drawn here. In RANS, the grid is extremely coarse. The cost is very less. So naturally, the accuracy will also be very less because you're not investing that much in the grid. LES, on the other hand, is slightly more expensive than RANS because it has to have a grid that resolves all the large scales. The cost will be slightly higher, and naturally, the accuracy will also be higher. DNS, on the other hand, is a full-blown solution of the Navier-Stokes equation. which means it gets U field for every realization. So the accuracy will be extremely high. It is the most for DNS, and the cost will also be extremely high. So those are the three approaches that we are going to be discussing in this module. And now when we are discussing these approaches, there are certain criteria for appraising these models and simulation approaches. And the principal criteria are the following. We will discuss each of these criteria in detail. So the principal criteria are the following. One is the level of description, and we sort of briefly described all of that in the previous slide. The level of description. To what level can these approaches describe your flow? Completeness. What does completeness mean? So when using any of these approaches, what in addition to these approaches have to be specified? How complete are they? You would think that DNS is fully complete. So because nothing else has to be specified, you just have to solve the Navier-Stokes equations. But for LES and RANs, how complete are they? That is what we are going to be discussing. Third is the cost and ease of use. We discussed that as well briefly, but we'll go into more detail. What is the cost of using this? How easy can we apply this? Range of applicability. Fourth one, range of applicability. Can they be applied to multiple kinds of flows? Fifth, accuracy. How accurate are they? And to look at all of this, we will consider two extreme approaches. One is the mixing length model, which is one of the first RANS type approaches that was developed. And I'll talk in the next class, I'll talk about in detail what the mixing length model is. And then on the other extreme is the direct numerical simulation or DNS, which resolves all scales and solves for U for every realization, which means it is the most accurate. So that's what I'm saying in the next point. The DNS consists of solving Navier-Stokes equations to determine U for one realization of the flow. So it is these that we are going to be discussing in next class. What is the criteria? We will discuss each of these criteria in detail when we are talking about the three approaches, DNS versus LES versus RANs. But mostly we are going to be looking at the two extremes in order to get an idea. So I hope this was clear. We will continue in next class. Thank you.